Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at rational and irrational numbers. So we really need to know the difference between these two when we come to do things like groups, fields, etc. So a number is said to be rational if it can be written as a fraction with an integer numerator and denominator. So using some logical notation and set notation, this says if x is a member of the rational numbers, so the rational numbers is denoted by this sort of double Q, that is true if and only if x can be written as a over b when a over b are integers. This basically just says for a number to be a rational number, you have to be able to write it as a fraction where numerator and denominator are both integers. Of course, if a number is not rational, then it is irrational. This, of course, means if a number is irrational, you cannot write it as a fraction with an integer numerator and denominator. It turns out that any terminating or recurring decimal can be written as a fraction and is therefore a rational number. So writing terminating decimals fractions is pretty easy. This is in the tenths, this is in the hundredths column. So this fraction is just going to be 24 over 100, which we can simplify as 6 over 25. So 0.24, as with any terminating decimal, it is rational because it can be written as a fraction. So what about recurring decimals? Well, remember, in exact form, we write this as 0.24 and we put a line or dots over that is repeated. So how can I write this as a fraction? Well, what we do this little trick here. We'll let x equal 0.24 recurring. So now what we're going to do is we're going to times x by something so that this new number has the same decimal expansion. So if we times x by 100, we simply move the decimal point 2 spots to the right. 100x will be 24.242424 and so on. It will also have a 2 and 4 recurring in that order. So then what would be 100x minus x? Well, that would be just 99x. So 99x is 100x minus 1x. So because these two numbers have the exact same decimal expansion, we can simply cancel it. 99x will be equal to 24. So if 99x is equal to 24, we can just divide each side by 99. What we get is x is 24 over 99, which of course simplifies to 8 over 33. Now you can use a similar trick for any recurring decimal. Of course, you might need to multiply it by a different number instead of 100, but you can still apply the same trick and we will see that any recurring decimal can be written as a fraction and is therefore rational. So we can update our understanding of irrational numbers to include the numbers that cannot be written as either a terminating or recurring decimal. Irrational numbers, their decimal expansion goes on forever because it's not terminating, but there's no pattern in the decimal expansion because they're not recurring. All right, let's now look at an important property of rational numbers. So it turns out rational numbers are closed under subtraction, whereas irrational numbers are not. What does that mean? What that means for rational numbers being closed under subtraction, if you subtract any two rational numbers, you will get another rational number. Now this is actually easy to prove because the definition of rational numbers means you can write it as a over b or c over d. It doesn't matter which letters you use. You can write rational numbers as fractions where we have numerators and denominators both equal to integers. So let's say I want to subtract them. Well, you know when we're subtracting fractions, we need to make the denominators equal. So I need to times top and bottom here by d and times top and bottom here by b. So then I get AD over BD minus CB or BC over BD. All right, so when we're subtracting fractions, of course, you subtract the tops and you leave the denominator alone. So the idea here is that this number here must be rational. Why is that? If you multiply together two integers, you get another integer. If you subtract integers, you get another integer, because integers are also closed under both multiplication and subtraction. So this here will be an integer, this will be an integer, so AB minus CD, the difference between two rational numbers, gives us a fraction with an integer as the numerator and the denominator. So that proves that rational numbers are closed under subtraction. If you take a rational number, subtract another rational number, your answer is rational. So we've proved that. But what about irrational numbers? We could easily show they're not closed under subtraction. So it's so much easier to prove that something's not true, because all you need to do is find a counterexample. So to show that irrational numbers are not closed under subtraction, I only need to come up with one example that shows that they're not. I only need to come up with one time where I can subtract irrational numbers and I don't get another irrational number. So a very easy example would be the square root of 2. The square root of 2 is irrational because 2 is not a perfect square. The square root of 2 is like 1.41 blah blah blah. It doesn't have a terminating or recurring decimal. You can't write this number as an integer divided by another integer. So if we subtract root 2 from itself, it's an irrational number minus another irrational number. We just get 0. 0 is rational, as are all integers. Of course, you could easily write 0 as a fraction, like 0 divided by 4. So what we've shown is if you subtract an irrational from another irrational, you don't always get an irrational answer. So this one example is enough to prove that irrational numbers are not closed under subtraction. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.